So far, we've discussed that prime numbers are numbers with exactly two divisors or factors, the number and 1, and that composite numbers are numbers that have more than two factors, so they have a factor or divisor different from the number itself and 1. We can express composite numbers as products of two or more whole numbers greater than 1. So for example, 6 is a composite number, and I can express it as 2 times 3. What we call this expression as a product of factors is a factorization. So one factorization of 6 is 2 times 3. When we use only prime numbers to factor a whole number, we call that a prime factorization. So if I think about the number 8, I can express that as 2 times 4. That's just a factorization because 4 is not a prime number. To express 8 as a prime factorization, I would need to do 2 times 2 times 2, or 2 to the third power. So something really interesting about composite numbers is that the fundamental theorem of arithmetic, or we can call it the unique factorization theorem, tells us that every composite number can be written as a product of primes in exactly one way, except for the order of the primes in that product. So if we want to find the prime factorization of a composite number, we need to rewrite the number as a product of two smaller natural numbers. And if these natural numbers are both prime, then we're done. So for example, when we talked about 6 being expressed as 2 times 3, 2 and 3 are both prime, so we were done. But when we said that 8 was 2 times 4, 4 wasn't prime, so we weren't finished. If one of the factors is not prime, then we rewrite it as the product of smaller natural numbers. So again, I said, all right, well, 4 is 2 times 2. So I would say 8 is 2 times 2 times 2. And then we just continue in that way until all of the factors are prime. Let's think through finding the prime factorization of 84. So the first thing you might think is I can divide 84 by 4, and I know that 84 is divisible by 4, and when I divide 84 by 4, that is 21. So I know 84 can be expressed as 4 times 21. Now, here I would ask myself, okay, are both of these numbers prime? In fact, neither of them are prime because 4 I can split into 2 times 2, and 21 I know is 3 times 7. Now I ask myself, all right, of these factors, are they all prime? Do I need to break any of them down anymore? And they actually are all prime because 2 is prime, 3 is prime, and 7 is prime. So I would write this as 84 is equal to 2 times 2 times 3 times 7. Or I can combine my 2's and say that 84 is 2 squared times 3 times 7. I can do the same thing to find the prime factorization of 495. So I know immediately that 495 is divisible by 5 because it ends in a 5 or a 0. So if I say, all right, 495 is divisible by 5, and I divide into 495, the result of that is 99. So 99 times 5 is 495. 5 is prime, but 99 is not prime because I know that 99 is divisible by 11. So I'd say, okay, 11 divides into 99, and the result of that is 9 because 9 times 11 is 99. Again, 9 is still not prime. 9 is composite because I can split it into 3 and 3. So I will write my prime factorization of 495. One way you could write it is you could say 5 times 11 times 3 times 3. However, the convention of how we write this prime factorization to make it unique is by saying the smallest factor first and then the next larger factors and combining our common those factors that are the same into exponents. So I would actually really need to write 495 as 3 squared times 5 times 11. Something you should notice about these factor trees is that there might be more than one way to go about splitting up your original number. So if I was splitting up 260, I could first split it into 26 and 10, and then split 26 and split 10 separately, or I could split 260 into 5 and 52 to begin with. Now, something that you should notice is that these two factor trees look different, but they produce the exact same prime factorization, because I would think of 260 in this case as 260 equals 2 times 2 times 5 times 13, or 2 squared times 5 times 13. And over here, I would say 260 is 2 times 2 times 5 times 13, because I have the exact same factors at the end of my tree. And this is also 2 squared times 5 times 13. Factor trees are one way we can go about prime factorization, but we can also go through factoring a number starting just by dividing with the least prime we can think of, and then try the next larger prime and the next larger prime and the next larger prime. So this is just a different strategy we can try for prime factorization. So let's start and take a look at 260. So I would start by saying, all right, what is the smallest prime number that is going to divide 260? I know that 260 is divisible by 2, and that's going to give me 130. And now I'm going to ask, okay, well, 130, can I divide it by 2? Sure can. It's going to give me 65. All right, so now I ask, okay, well, what's the smallest prime number that's going to divide 65? 2 does not divide 65 because 5 is odd. 3 does not divide 65 because 6 plus 5 is 11. 11 is not divisible by 5. 5 should divide 65 because 65 ends in a 5 or 0. And 65 divided by 5 will result in 13. And 13 itself is prime. So now I see I have my primes, my factors, all laid out for me. So I've got 2, 2, 5, and 13. So 260 is 2 times 2 times 5 times 13, or 2 squared times 5 times 13, which is the same result we got from our factor tree.